So welcome to a review session on the thermodynamics course. So in the past weeks we have seen numericals on each of the weeks and how to solve those. So this today's session will be on a review session before exams. So we will go through the concepts which was the major concepts which was taught over the course, and I've prepared slides on the concepts and not on problems. So we'll go over the concepts. So starting with thermodynamics. Uh, give you a brief introduction. I will start from start. So thermodynamics. So thermodynamics is science which deals with the study of matter as well as that of all phenomena involving work, heat, and energy uh, occurring with that matter. So that's what basically thermodynamics is. So you consider some matter and you see the phenomena or the processes happening in that the matter which you are intent to study. So that is thermodynamics. In generally speak, the word thermodynamics, it comes from the Greek word therm and dynamics. Therm is heat and dynamics is force. So the study of thermodynamics evolved to generate work from heat. So that pushed the boundary for creating thermodynamics, and thermodynamics in general, uh, based on what your study intent is, could be a macroscopic study or a microscopic study. Microscopic in terms, macroscopic you have phenomenological study, because you take the system in bulk, you have quantities, and in statistical, microscopic level, you can go with the statistical thermodynamics, and where you study the molecular level thermodynamics, and it involves probability calculation and how the atoms are arranged in their energy levels and so on. That it gives you a statistical thermodynamics. What we will be looking, or what we covered over the weeks of the study, all involved macroscopic study. Or macroscopic study requires that a continuum to exist in the matter which you are studying. So what is continuum? So continuum, you have suppose you have a space where you assume which you are considering, you are putting some 10 molecules of any substance, or 10 atoms you have put. So if you estimate a density, so at some point you may have zero density, because the space which you are considering, the 10 molecules are very small. So you'll have a very your density variation will be large. So at any point of time you may have one or two atoms in your study space, or it may be zero. So if you go and keep on adding these molecules, so at a certain point of time it will happen that, so from initially you have 10, now you increase to 100, then 1000 or something. If you keep on increasing the molecules, and you measure the density. So density is whatever volume you are considering, and the molecules, the mass of the molecules present in that region which you are considering. So if you keep on increasing the number of molecules, a point comes where your density oscillations will be less. So previously when the molecules were less, say any number of molecules can come inside the region, go out in the certain region of space which you are considering. So in that case your density oscillations were large. So now at a point when you keep on increasing the atom, a point will reach where this density variation is still less. You consider after this point as a continuum, that your density variations are less, and you say that it is in continuum, and that kind of matter study is what we use for a macroscopic study. And as I told previously, a microscopic, you go into molecular level and study those. So having an idea on the thermodynamics and what we are studying in this thermodynamics, moving on, as I told previously, thermodynamics has evolved to study to create work out of heat, and generate work out of heat. So To do that, we need to consider system or the matter. As told, the thermodynamics is study of matter. So there are some certain terms defined. So I'll just go over those terms to brief you upon that. And system, as we have already seen, system is a whatever we want to study, and the shape or volume of the system being analyzed is not necessarily constant. So as can say in a compressed cylinder, your volume is changing, but there the mass is constant. So your shape or volume may differ. So that is system. Then surrounding is whatever you are studying. Apart from that, whatever is outside that is your surrounding. So everything external to the system is considered to be part of the system surrounding. Then boundary is nothing but one which distinguishes this system and surrounding. So if you say you have inflated a balloon and that is your system, so that balloon will be your boundary. Whatever air which is there inside the balloon, that is your system. That balloon you can consider that is your boundary. And then outside the atmosphere, it's your surrounding. Then the system can be of two types, or a closed system or an open system. And you have also a special case which is an isolated system. So if you see a closed system is nothing but is defined when a particular quantity of matter is under study, and a closed system always contains the same matter. So it is in sense it's closed. Anything can come or go out. The matter which you are present, the mass will remain same, and whatever is going present inside, it will be there. There is nothing coming in and nothing going out. So a closed system is a closed system for matter. So there is no transfer of mass across its boundary. But in a closed system, you can have energy transfer. Second case, the special case is an isolated system. So this is a special type of closed system that does not interact in any way with its surrounding. So that says that it cannot have energy transfer, that is in form of heat and work, and it cannot have any mass transfer. Then you have an open system. Open system is also called as control volume, and closed system can also be called as control mass. So your mass is constant, so control mass. Here control volume, your volume is constant. So your mass can vary, but in a region of space you consider some volume. So that is your intent study. That volume will remain constant. That is called as control volume. So if a region within prescribed boundary is studied, the region is called a control volume. So mass cross the boundary of a control volume, and you can also have energy transfer. So in open system, you have both the mass transfer as well as energy transfer. And if you see in closed system, there is no mass transfer, but can be a control energy transfer, and your volume can change. And in isolated system, it's a special case where you don't have any transfer or interaction with the surrounding. Next, we know a system. So we also know the type of system. So how will we define a system? So we define a system based on a property. So property is a macroscopic characteristic of a system, such as mass, volume, energy, pressure, and temperature. So these are all properties of a system. So it's called as state properties or state functions, to which a numerical value can be assigned at a given time without knowledge of the previous behavior. So this is important. So the property, it doesn't matter what it was in the previous, or history of the property doesn't matter. So at any instant, it will have some value, and that defines the system. Its history doesn't matter to the current state for the property of the system. So property is a macroscopic characteristic. It's just like a person's to define a person is weight, height, or name. So it's like that. Property system property is like that for the system. So property is a macroscopic characteristic of a system such as mass, volume, energy, pressure and temperature, for which a numerical value can be assigned, and without any knowledge of the previous behavior or history of the system. So the word state, so is like how the system is at current point, so that defines the system, so that is called a state. So state refers to the condition of system as described by its property. So for any state you will have a certain property and that defines the system, and then when any of the properties of system changes, the state changes and the system is said to undergo a process. So if system is undergoing something and the values of the properties changes, that defines that your system is undergoing a state change, or it's undergoing a process. The system is said to be a steady state if none of the properties changes with time. So with respect to time, your so system is said to be not vary. So in that, if it doesn't vary with respect to time, you say that it's in steady state. But that doesn't mean that your system is not undergoing anything. So or say if your there is some amount of mass, 1 kg of mass coming in and 1 kg of mass going out, whatever there in the system will remain same, but this is, you can say, it is in steady state. So a property, next is a property is called now we know a system, we know state, we know property, and this property can be of two types. One is called an extensive property and one is called an intensive property. So extensive property is an overall system value of the system and some of its value for the parts into which system is divided. So it is dependent on mass. You can say extensive property are mass dependent and intensive property are independent of mass. So how do you distinguish between an extensive and intensive property? You take any property and for a system consider that property and divide the system into half or any ratio, and if you see any change in the value of the property for individual portions, then you say that it is an extensive property, and if it doesn't change, then you call it as an intensive property. So again, for example, if you go if you take water and you suppose you take 1 kg of water, you know density of water is 1000 kg per meter cube. So you can say if you split the water into half or any portion, you will see the density of water will remain the same irrespective of what proportion you are splitting the water into. But if you take mass or volume, it will change. So that is an extensive property, and if you see density, it's an intensive property. Similarly, temperature, if you say temperature is an intensive property. If water is at any temperature and if you split that water, the overall bulk value of the whatever the portion of the water is, it will still be at the same temperature. It will not vary. It may at molecular level it may vary a certain point, but overall if you calculate the bulk in a macroscopic view, your temperature will be, the average value of the temperature will be same. So again, that will be an intensive property. So these are some examples of the system. So if you say first one is a closed system and it's insulated, so adiabatic, so this will be an isolated system. So second case, you have closed system but it's not insulated, but so it can heat transfer, so it's a closed system. And again third one again is a closed adiabatic, but your volume is varying, so some work transfer is happening, so this is closed system. So these are some examples which I covered in the first week, so you can go through and see the first example. So this is the simplest example of showing all three cases of closed, open and isolated system. So if you have a thermos flask and you have a tea and it's a hot tea, and if you have it in a thermos flask, it's closed, so there is no mass transfer which is happening, and tea is your intent of study. So that is your system. So there is no heat transfer, there is no work transfer, and there is no mass transfer. So that will be your isolated system. Now if you pour it in a cup and saucer and keep it outside, so in that case there can be a water, this tea which is getting evaporated, so there will be mass transfer which is happening, and also the heat will also be, because after some time the tea will get cold, so there is some heat transfer, which is the heat is lost from the tea. So this is an open system, and if you put a lid up, so now you have closed it, so it's a closed system, but there is still heat transfer, there is no mass transfer, so it's a closed system. So your thermodynamics can use it to study anything from a small system to large power plants in this thing. So if you see this huge power plant which I covered in the first week, so this you can make it into a small control volume, so covering the whole power plant, and you can just study what is coming in and what is going out to get an idea of the power plant. So this power plant we saw you need coal and air to burn it, and you're producing energy. So that is in terms of mass which is coming in. So coal is coming in, combustion air is coming in, and the burnt gas is going out as flue gas. So there is a mass transfer, and you are using that heat to also do a district heating. So there is water coming in and getting heated and going out. So the cold water and hot water is coming in for district heating, and whatever heat is generated is used to produce work. So that work is converted into electrical energy and is taken out as electrical work using a underground power cable. So if you see, you have simplified the whole system into just whatever is coming in and coming out. So using this we can estimate and calculate what the power plant is, or the efficiency of power plant, and so on. So we have seen a system or a state and so on to define it. So the other part is to know whether it's in equilibrium. So the state of a system in which the properties have definite unchanged value as long as external conditions are unchanged is called an equilibrium state. So if your system doesn't change with value and it's definite, so that it is called as an equilibrium. So this equilibrium can be of three types. One is in mechanical equilibrium, other is thermal equilibrium, and third is chemical equilibrium. So mechanical equilibrium is nothing but there is no unbalanced forces, and there is no force acting, so that is mechanical equilibrium. Thermal equilibrium, there is no temperature difference, there is no heat transfer which is happening, and that is thermal equilibrium. And third is chemical equilibrium. Chemical equilibrium, again there is no reactions or phase changes which is happening, then that is chemical equilibrium. So we saw what is processes. So undergoing a change of state is a process. So the state from to a change of state is called as process, and the path across which the states are changing, that is called as a path. And when a system comes back to the initial state, that is called as a cyclic process or a cycle. So next is an quasi equilibrium process. So we know process. What is this quasi equilibrium? Quasi equilibrium means tending to equilibrium, or say as if it's in equilibrium. So if a process involves finite unbalanced forces, the system can pass through non-equilibrium states which we cannot rate. So an extremely useful idealization, however, is that only infinitesimal unbalanced force exists, so that process can be viewed as taking place in a series of quasi-equilibrium states. So what this says is, this all comes in the to avoid the concept of the entropy. So you making the system irreversible. So if you have a large unbalanced forces, it can go to a non-equilibrium states, which it's difficult to calculate or uh, take into account for. So what we assume is that system goes through a small changes, and each state is an equilibrium state. So we have very small unbalanced force, or that's an infinitesimal small change, and you take the process to occur. So that is called as quasi equilibrium state or a process. To avoid uh, the non-equilibrium states to have occur. So the major two energies which are involved in the study is the heat and work. So heat, we know, heat is a form of energy that is transferred across system boundary due to temperature difference across the boundary between the system and the surrounding. So this implies that heat is a form of energy transfer. Heat is experienced only across the system boundary, and substances do not contain or store or gain or lose heat. So heat cannot be stored. Heat is something which is occurs at the as a transfer. So it is occurring at the boundary. So heat doesn't is not getting stored. What is getting stored is stored as energy, not as heat. Heat is something which is moving. It is always it is in transfer. So the important thing is the sign convention. We assume that heat is positive when the heat is transferred from surrounding to the system, and we consider heat is negative when heat is transferred from the system to the surrounding. So whatever you receive to the system, what you are studying the system, if it receives heat, we consider that as positive, and if it rejects heat, we consider that as negative. Then comes work. So work is a form of energy that is a result of force acting through a displacement, or in general in thermodynamic study we say work is done by system on the surrounding if the sole effect on the surrounding is the raising of weight. So whatever may be the form, we equate that to a system which is equivalent to raising a weight. And the work expression, you can get as integral p dv. So that comes from force into displacement, and force you can write as pressure into area, and area into displacement will give you volume, change in volume. So that, if you see, that is equivalent to the definition of work which was defined as raising a weight. So this work definition which we got from the statement. So if you see, work is again energy transfer, and work is experienced only at the system boundary, and they also don't store or gain or lose work. So if you see, work is opposite of this heat. So in terms of how we consider positive and negative, so here the work is positive when we receive it from the system. So again, this all sign convention came because I told previously, the thermodynamics, the idea is to convert heat to work. So that's why heat when giving you are positive, and work when you are receiving positive. So the intent was to generate work. So hence the output what we required was work, and we consider that as positive, and work as negative when the work is done on the system. So we saw heat and work, and the functions also, the property when we define sorry. So these are there are something called a state function and path function. So state functions are properties define this thing which are based on the state, and it doesn't have any impact on the history. Heat and work are path functions. So these values differ on the process which is occurring, or the path the system is going through. So which we see in the previous the quasi equilibrium states of or the process which is happening. So the path that process is happening gives you changes, then the heat and work value will also change. So with that, the process can be of three types. One is reversible, irreversible, and quasi-reversible. If after the process of restoration, so reversible is a process when you can go back to the previous state. So it's if you are starting with some process, some state, and a process occurs and you reach some state B. So if you can trace back to the state A uh, wholly, that your surrounding and your system, everything changes back to state A, that is called as a reversible. And irreversible is something which you cannot make. So if even if you go back, there would be a difference in what you started with. So even though you would have achieved in a system, you could have not achieved in a surrounding. So then that is an internally reversible and irreversibility externally. So a quasi-reversible is something which is close to reversible. It is not fully reversible, but you consider that it to be reversible. So some of the phenomena which causes irreversibility is heat transfer through a finite temperature difference. So we know we'll go through a second law which explains why this is happening, and then unrestrained expansion of gas, vapor, liquid to a lower pressure. So again, unrestrained expansion, if you have something which is expanding and you are not getting anything out of it, but you have to take it back to state A, you have to do work to make it into. So if you have balloon and you release that balloon and air escapes, you cannot bring that inside to the balloon, so that is not possible. So you have to do work to push that what has expanded back into the balloon. So that defines irreversibility. So if you could do it without any intervention and go back to the previous state, that is reversible. So in friction between solid, liquid and gas, or within a fluid. Next is mixing of two different species of molecule. So if you have something two gases which you are mixing, so again separation requires some work to be done. So that is irreversibility. So heating by passing an electric current, so that is again an irreversibility. Inelastic deformation. So these all are some of the examples which can make a system irreversible, which makes a system irreversible. If the irreversibility occurs within a system, then it is categorized as internal irreversibility. On the irreversibility, if it is occurs around the surrounding, that is an external irreversibility. So now going to the law of thermodynamics. So in thermodynamics we have three laws, but in the course we studied two laws till second law. So out of all, the first law is the zeroth law of thermodynamics. So if two bodies are in contact through a thermal conducting boundary for a sufficiently long time, no further observable change takes place. So that says that the system has come into thermal equilibrium. So example is, you say a thermometer, you take and measure your body, that's the easiest of all. So uh, you put a thermometer, uh, any thermometer. So previously you used to have that mercury thermometer, but now there are digital thermometers. So if you put and in your body, near your body, and you let the thermometer to come into thermal equilibrium with the body, and that gives you the temperature. So zeroth law of thermodynamics gives you uh, the concept of temperature measurement. So two systems which are individually in thermal equilibrium with the third are in thermal equilibrium with each other. So that is saying that A is in thermal equilibrium with B and B is in a thermal equilibrium with C. Then you say that A is in thermal equilibrium with C. So that was essentially zeroth law says. So there exists for every thermodynamic system in equilibrium a property called temperature. So this equality of temperature is a necessary and sufficient condition for thermal equilibrium. So zeroth law gives you the concept of temperature, and this says that if this temperature is same for the bodies which are in thermal equilibrium, that is necessary and sufficient condition for to say that both are in thermal equilibrium. And this uh, bodies which are in thermal equilibrium may not be identical. Even though they are in thermal equilibrium, their temperatures will be equal, but they may not be ideal. So if you want to say uh, you have some pressurized gas which is there in a container, and this container gas pressure may be different. So it be because it's a pressurized gas, so assume that it should be some 10 bar or something. This temperature will be equivalent to your ambient temperature. So if it's not insulated, so that temperature will be equal to your ambient temperature. So that pressurized cylinder is in thermal equilibrium with your ambient surrounding. uh, so but if you see, the states of each of the system and the surrounding are different. So uh, even though these are in thermal equilibrium, but these two systems are not identical. So that you should keep in mind. uh, then once zeroth law is defined, which gives you the concept of temperature, uh, then comes the first law of thermodynamics. First law of thermodynamics says that it's a conservation of energy basically. So the first idea of first law of thermodynamics came uh, from the Joule's experiment. So if any system goes through a cycle, then it says that whatever heat is transferred, the net heat transfer is equals to the net work transfer. So your summation of heat transfer is equal to summation of work transfer, or you can say cyclic integral of Q is equal to cyclic integral of W. And then the first law stated that see, if I want to go through two states and not a cyclic process, then this net change in difference in the heat and work transfer which is happening, that goes into raising the energy of the system. So you are supplying some Q, you are taking some away some energy as work, but the energy, there is a Q and W both are energies. So this difference in energy should be going somewhere. So that is going inside the system, raising its own energy. So that is defined as the internal energy. So this is how the first law will come out to be. So delta E is equals to Q minus W. So that is your first law. Then in most of the cases where we deal with, we assume that for the system the internal potential energy and kinetic energy are negligible, and there is no chemical reaction or chemical energy of the system. So we all neglect that, and then the delta E becomes to equal to, the energy becomes equals to the internal energy delta U. So now if you see that it becomes delta U equals Q minus W, or if you write in terms of specific energies, so specific again is an intensive property, so delta small u equals Q minus W. So if you see, even though Q and W are path functions, their difference gives you delta U, which is a state function. So delta U is not independent of is independent of path, and it just requires a state value. So U is a state function and Q and W are path functions. So now we saw zeroth law and first law. So before going to second law, we'll see, we'll try to because first law is a conservation of energy, so we'll see how to apply a control volume and how to study that control volume. So now if we suppose this is my control volume, and there is some amount of mass which is coming in and some amount of mass which is going out, and the internal box is my region of study, so that is my control volume. So you can write it in say m which is coming in and in some rate form, and come derive it, and the simplest way is to say that physically you can intuitively write this expression, so that we have some amount of mass which is coming in and some amount of mass which is going out. So if that is not equal, then that mass is getting stored in the system, right? So this is what we get. So dmcv by dt is the rate of change of mass in the system. So how much is the mass getting rate, at what rate that mass is getting stored in the system, that is equal to nothing but mass which is coming in and minus mass which is going out. So straight away we will get an expression for conservation of mass. Then at a case where your inlet mass and outlet mass is same, then it says that your in dmcv by dt will become 0, then mass which is coming in should be what it is going out. So nothing will get stored, whatever was there inside the control volume will remain same, it will not vary with respect to time, so that will become a steady state. So mass which is coming in will go out, so m dot in equal to m dot out. So if you say steady state, then with respect to time that becomes 0, so which is coming in should be equal to go other which is going out. Or the other way, if you say my what is coming in is equal to what is going out, then that gives you steady state. So you can see it either way. Next we have conserved the mass. The next is to conserve an energy of system, or the energy interactions which is happening. So similar to what we saw, we can apply the same concept here. So energy is in of two forms, one is heat and one is work. So the net difference between this is what increases the energy inside the system. So the rate of change of energy within the system is equal to the net energy transfer. It could be in either form, so Q minus W. So that is equals to the net change in energy of the system. So this we are doing it for a closed system. Suppose instead of a closed system, I had a open system. So here there is no mass transfer. So if we have an open system and we have mass transfer, then we have to write a flow energy equation, steady flow energy equation. So then this is how it will look. Suppose this is my control volume, and if you see there is some amount of mass which is coming in, which is at pressure at P and T, PITI, and energy EI. And similarly specific volume Vi, and there is some amount of mass which is going out, and there are different kinds of work which is happening. There is boundary work, there is a shaft work, and then there is a heat transfer which is happening. So if you all account it for, so this is how the simple equation will be: the rate of change of energy in the control volume. So this is what we did in the previous example of the control mass. So rate of change of energy in control volume is equal to rate of heat added, the net heat added. So there can be heat which is removed. So the difference, the net heat added minus rate of net work done, is what for the closed system. But in the open system, you are again having some interaction with respect to the mass. So the rate of energy flow into the control volume with because of the mass minus rate of energy which is flowing out of the control volume. So if you see, because of the mass flow, what is the energy which is it bringing? So it is equals to E plus PV, or the enthalpy. So E you can write it as U plus kinetic energy, potential energy, and plus PV. So PV is nothing but the boundary work which is happening for it to enter. Then it is equal to H plus C square by 2 plus GZ. So you can substitute that. So dEC by dt equals Q dot Cv minus W shaft plus mass m dot I into the enthalpy, kinetic energy and potential energy. And similarly for mass which is going out, minus m dot E Hc plus C V square by 2 plus Gz, that is the potential energy. So if you see here, dEC by dt, whatever is coming in we are taking it positive, and whatever is going out we are taking it as negative on the right side. So dEC by dt equals Q is coming in is positive, so minus W which is going out plus m dot I into the enthalpy which is coming in minus m dot E which is going out into enthalpy of the fluid which is going out. So that is the expression, and you can get the previous expression for control mass straight away from this expression. If you assume the mass which is going in and coming out as 0, so you can get that previous expression. So this is called as a steady flow energy equation. So in steady flow energy equation, with respect to time, the rate of change is 0, so dEC by dt will become 0. So that is not varying with respect to time. So this the expression which this is the expression which you will get, and you can write it in terms of specific values. Then it's nothing but Q minus W is equals to enthalpy out minus enthalpy in, and also the potential and kinetic energies. So an example of the previous expression applying. So this we have did multiple examples on the tank filling on this thing on the corresponding week. You can go that and check it out how to solve this. So just to give you a brief and to brief you on that, I have taken this example. I not solved anything, but just giving you the concept how to solve. Go ahead and proceed to solve. So this problem, this is my control volume. There is some amount of mass which is coming in. So I am filling this tank with some gas or fluid. So that m dot mass is coming in. So and then my tank is my control volume. So in this case, if I apply an energy balance, so if I go back to the previous example, so ECV is becomes UCV. I am neglecting kinetic energy and potential energy. So du Cv dt, and in this case my across tank I am not getting any work, I am not getting any heat transfer, and there is no exit mass. So there is only mass which is entering. So there is only mass which is entering. So the previous SFW becomes du by dt. The Q is 0, W is 0, and m dot E is 0. So I am assuming kinetic and potential energy is 0. So this becomes du by dt equals m dot I into Hi. So and you can straight away go and find this, and if you apply a mass balance here, so mass inside what is varying is the rate of change mass which is entering. So you can use this to solve to find out temperature or the enthalpy of the system or whatever been asked the question. So this is how it will reduce. So another example is a flow through a rocket nozzle. A similar you can straight away apply this. We can assume there is no external work which you are getting, and we assume it is an adiabatic process. So my Q and W both will be 0. So this will reduce into m dot into enthalpy out minus enthalpy in through the nozzle. So if my nozzle entry is from the combustion chamber, I'll use that Hi and Ci is the energy which is entry to the nozzle, and exit is denoted by E. So from this, enthalpy is nothing but Cp into T, and from this we can estimate the velocities of the fluid or the rocket from the exit velocities. And again, strip ahead, if we don't know temperature, if we are the pressure is given, this being adiabatic, we can assume it is an adiabatic expansion, and we know for an adiabatic expansion it's nothing but Te by Tc equals P by Pc raised to the gamma minus 1 by gamma. So from there we can get that. So that are examples of how to apply in steady flow energy equations. So we have seen zeroth law, first law. Next is the second law of thermodynamics. So as I told previously, zeroth law of thermodynamics defines the temperature, and your first law of thermodynamics defines your energy, conservation of energy, and the second law of thermodynamics came into practice because so thermodynamics was derived because we need to generate work from heat. So we were any amount of heat we supplied, we were not able to get all the heat into work. So there was some limiting case, and also the first law couldn't explain a process whether it could be possible or not. So then second law of thermodynamics were invented. So for example, you have a hot cup of tea and it gets cold, but you cannot make it hot. So you need a property which says whether that process can happen or not. So that was done by a second law of thermodynamics. So your entropy was defined as dq by T, dq reversible by T, and it's the Clausius said that the cyclic integral of dq by dt should always be less than or equal to 0, and since dq by T is entropy, so your entropy will be should be greater than or equal to 0. So it should always be greater than or equal to 0. So at for if your whole cycle or the process is reversible, then your entropy change ds will be equal to 0, or if it's not irreversible, then your entropy will be greater than 0. So this allowed us to study any process and say whether the process can proceed this way or not. And then using this concept, Kelvin and Planck and Clausius gave two statements on second law of thermodynamics. So Kelvin-Planck statement goes like this: so no process is possible whose sole result is the absorption of heat from a reservoir and the conversion of this heat into work. So that basically says that whatever amount of Q heat you are getting, you cannot convert the whole amount of Q into work. So you have to reject some amount of energy which you are getting to another reservoir. So basically you cannot operate with a single reservoir. So that's what Kelvin-Planck statement said. And then Clausius statement. So Clausius said that no process is possible whose sole result is the transfer of heat from a cooler to hotter body without giving work. So what he said is you cannot transfer cold from a cold body to a hot body. So you cannot transfer heat from a body which is at lower temperature to a body at higher temperature without supplying any work. So that's what Clausius said. So this any violation of a Kelvin-Planck law will also violate Clausius statement. It's the either way around. If out of any of these two statements one is violated, it will automatically violate the other. So this both defined the second law of thermodynamics. So if you using the inequality term, so we know for a reversible process, ds is defined as dq reversible by t. So if you have an irreversible process, how will you write an entropy expression? So for that, you can write convert the inequality. So we said that ds should be greater than or equal to 0, and ds should be greater than or equal to dq by t, integral dq by t. So for a given process, you are converting that inequality into equality by adding a term called as delta S generated to account for the internal reversibility of the system. So if you apply for any control volume, you can do an entropy balance thing, so which says that summation of q by t, the heat transfer occurring across the control volume, divided by the corresponding temperature, plus the entropy which is coming in minus entropy which is going out, plus S generated is equals to the change of rate of change of entropy within the control volume. So this again is similar to what the first law expression which we wrote. So the rate of entropy generated because of heat transfer, plus which is coming in minus going out, plus the S generated, this is to account for internal reversibility. This is equal to the rate at which the entropy is changing in the control volume. So this, with this you can do an entropy balance. So next is in a Carnot cycle. So Carnot cycle was invented by Sadi Carnot to find out what can be the maximum possible work which you can generate from the any heat engine. So his idea was to see what is my limit where I can get the maximum out of an engine. So then he came up with a idea of creating an ideal cycle which is totally reversible, and then create estimate a value or efficiency of a cycle which gives you the maximum possible work which you can extract from a heat engine. So with that he created a Carnot cycle. So this is how a Carnot cycle works. So before going to cycle, I'll also define the processes, what is happening. So and you can define for any process in isentropic efficiency. So isentropic efficiency is nothing but your process is, you assume that it to be a reversible adiabatic process, that is called as an isentropic process, or in that process your entropy is constant. So reversible adiabatic is also equivalent to saying it is an isentropic, or your entropy is constant. When your pressure is constant, it's an isobaric. When your volume is constant, it's an isochoric. When your temperature is constant, it's an isothermal. Where your enthalpy is constant, it's an isenthalpic. And when there is no heat transfer, it's called an adiabatic. And if you have no reversibility, internally reversible, then again ds is 0 and it's called an isentropic process. So with this your compressor and your turbine, you have efficiency, you assume your turbine and compressor to work as isentropic processes, that is reversible adiabatic process, but actually they don't work ideally. So you define isentropic efficiency. So isentropic efficiency is the turbine work, real turbine work divided by isentropic turbine work, and in terms of compressor, it's the reverse of that. So isentropic compressor work divided by the real compressor work. So with that we'll see Carnot cycle. So Carnot cycle is, you have 4 processes. So Carnot came up with this idea of having reversible processes. So with that it is isothermal expansion, and then so sorry, I'll go with 1 to 2 isothermal heat addition, and then 2 to 3 isothermal expansion, and then 3 to 4 isothermal heat rejection, and 4 to 1 isothermal compression. Practically speaking, this is very difficult to achieve. One, because you can try to build it, but the problem is you cannot have isothermal heat addition and work done, it's very difficult to have both heat and work transfer in case of isothermal process. The process will be very slow, and the system will be becoming bulky. So that is one of the limitations of Carnot. It will also, if you practically speaking, you cannot approach. You may try to approach reversibility, but it's very difficult. So there's a limitation which is coming into play, practically speaking. So Carnot cycle says comes from applying both your first law and second law. So second law says that your integral of delta q by t should be going back to Clausius inequality, delta q by t should be less than or equal to 0, and for reversible process should be equal to 0. So that what is applied to a Carnot cycle. You assume that all 4 processes are reversible, then your delta q by t is 0. So in the Carnot cycle, so you have heat addition and heat rejection occurring at a constant temperature, which is Th and Tl, or you can say T1 and T2. So that becomes Q1 by T1 plus Q2 by T2 equals 0. Then I can take Q2 as a negative here. If you are assuming it to be rejected, then becomes Q1 by T1 equals Q2 by T2. Then this also says the limitation where you say Q, when you want to convert the whole amount of Q into work, then you have to reach temperature of 0 Kelvin. So that is that comes to the third law. Third law says that you cannot reach 0 Kelvin. So that is other limitation. Then heat transfer, your efficiency from this you can get as work is, if you apply first law, then your work done is nothing but your net work done is equal to net heat transfer. So your net work done is W. So that is only work we are coming out, there is no input. So W is equals to net heat transfer, which is Q1 minus Q2. So your efficiency is nothing but your output given to the desired input which you are giving. So your desired output is work. So W by Q1. So W can write as Q1 minus Q2. Then we will ultimately end up with this expression of 1 minus T1 by T2, which is for the Carnot cycle efficiency. So this efficiency is the maximum efficiency which you can get, and Carnot cycle is for any temperature level. If you run multiple Carnot cycles, each will have the same efficiency, and it is irrespective of fluid. So whatever you don't care about what fluid is it, but it only depends upon the temperature levels. So going on to next, you have Otto cycle. So Otto cycle is if you practically speaking, it's called an what you see is a petrol cycle. So petrol engines. So work in Otto cycle. So again here you have 4 processes. So those are 1 to 2. You have a reversible adiabatic or isentropic compression. Then 2 to 3 is a constant volume heat addition, and 3 to 4 is again reversible adiabatic or isentropic expansion, and 4 to 1 is heat rejection, and that again is occurring at constant volume. Again other case is a diesel cycle. In diesel cycle, the only change is the heat transfer is occurring at constant pressure instead of constant volume. So again in Otto cycle, your net work done efficiency you can define as work done divided by heat input. So work you can again get by QH minus QL. The QL is positive because you are taking negative which is going out as minus QL. So to take the value is positive, hence you are getting plus QL. So if you take QL as absolute value and going out as a negative, it becomes QH minus QL by QH. So from there you can find out the efficiency. So similarly work done is nothing but integral CV dt between two temperature T2 by T3 So because this is occurring at constant volume, this will become Cv T3 minus T2. So that gives you the heat transfer, and QL is nothing but Cv T1 minus T4. Again, that is because it's occurring at constant volume. So using this, when you substitute, your Otto cycle efficiency will become 1 minus 1 by R gamma minus 1. R is nothing but your compression ratio V1 by V2. So this gives you the Otto cycle efficiency. And similarly, for a diesel cycle, you have a same expression. You can find out work done by heat input. Heat input is QH, and here QVL, heat rejection will be same, which is Cv T4 minus T1, but your heat addition is at constant pressure, so it will be Cp T2 minus T3. Sorry, Cp T3 minus T2, and then we can substitute in the expression, and it will reduce to 1 minus 1 by gamma into R gamma minus 1. Gamma is your Cp by Cv value into Rc raised to power gamma minus 1 and Rc minus 1. Here Rc is the cutoff ratio. Cutoff ratio is V3 by V2, which is the volume ratio in the heat addition process, and R is your compression ratio V1 by V2. So this gives you diesel cycle efficiency 1 minus 1 by gamma into R gamma minus 1 into Rc gamma minus 1 by Rc minus 1. So this is complicated. You can straight away find out QH and QL and find out the efficiency. That is a easier way you can find if you know the temperatures. If you start with if you know just the value of volumes, so you can find temperature and proceed that way, or you can straight away apply the efficiency formula. So after Otto and diesel cycle, there is also a combined cycle between Otto and diesel that is called a dual cycle, where the heat addition process occurs in two steps, as you constant volume and then constant pressure. That we can use the same approach and proceed further. Then moving on, we have Brayton cycle. So Brayton cycle again has 4 processes. So and it can be of 2 types. One is an open cycle and it is a closed cycle. So if you see, you have isentropic compression, and then isobaric heat addition, then isentropic expansion, and isobaric heat rejection. So if you see, it's if you in diesel cycle, your addition was constant pressure, so you can have to just extend it, and you say rejection is also isobaric. So Otto, you had both constant volume isochoric process and 2 isentropic process. In diesel, you had 2 isentropic, 1 isobaric and 1 isochoric. In Brayton, you have 2 isentropic and 2 isobaric processes. So again, efficiency is nothing but you know both the QH and QL. You can find out heat addition and heat rejection. This will be at constant pressure. So Cp into delta T, and from there you can find out the net work, which is the difference in heat transfer. So because this is occurring in a cycle, so net heat transfer is equal to net work transfer. So you can use the net heat transfer to find out which is equal to net work, divide by the heat in. This gives me 1 minus Td minus Ta by Tc minus Tb. So from this you can write in terms of the pressure ratio or the temperature ratio. It will come out to be your Brayton cycle efficiency is 1 minus Ta by Tb. So since this Td by Ta is equals to Tc by Ta, because this isentropic expansion, your pressure raises are same for both the expansion and compression. So from there you can cancel out the bracket terms. So it will come out to be 1 minus Ta by Tb, which is the compression temperatures, inlet and outlet of the compression temperatures. So from that you can straight away find out Brayton efficiency as 1 minus 1 by your temperature ratio, or in terms of pressure ratio 1 minus 1 by pressure ratio raised to power gamma minus 1 by gamma. So next is before going to Rankine cycle. So Rankine cycle is an occurring in two-phase region. So we need to find out the properties defined for a two-phase system. So if you see, this is your saturated liquid line and saturated vapor line, your two-phase dome, and for any process occurring between A, B and C, so that's your phase change. If you say constant, this is a PV, it's plotted in a PV diagram. So for constant temperature line looks like this. So in the left you have a liquid, and in the right you have a single phase vapor, and inside the dome you have a two-phase mixture of liquid and vapor. At the top you have critical point, and the left line is a saturated liquid line, and your right line is a saturated vapor line. And for any temperature T, the state A is a saturated liquid, state C is a saturated vapor, and B is any mixture state. So from there the saturated liquid is defined a specific volume Vf and Vg. Then for total mass of the system, if you see at point B is the liquid mass plus vapor mass, and your volume of the liquid is nothing but mass of liquid into the specific volume of the liquid, saturated specific volume. And similarly for vapor, the volume of vapor is mass of your vapor into the specific volume of the vapor. So from this you can find out the total volume. So from this you can, if you see, specific volume is nothing but mf Vf plus mg Vg divided by the total mass. So that gives you a specific volume. If you see, you can derive a factor called dryness fraction, or the quality, that is nothing but the mass of vapor divided by the total mass. So from this you can get specific volume as x into your vapor specific volume plus 1 minus x into your liquid specific volume. And similarly you can define it for any other properties, internal energy or enthalpy or so on. And for Rankine cycle, this is how a Rankine cycle works. So your it's like equivalent to a Carnot cycle. So but there you had Brayton cycle. So you have two isobaric process, but here it's inside your vapor phase dome or two-phase dome, and 1 to 2 is your isentropic compression, isentropic expansion. 2 to 3 is heat rejection. 3 to 4 is isentropic compression or pumping, and then 4 to 1 is heat addition. So for 1 you have vapor which you are expanding in the turbine, and then you are rejecting that excess heat, and then you are pumping back into the boiler where you are heating it. So this is how a Rankine cycle works. So you can apply individual component control volume and can find out what is the energy happening. So Q in is nothing but if you apply control volume across the boiler, so there is mass m which is going in across the cycle, so per unit mass, so equals the enthalpy which is coming out minus enthalpy which is coming in, so H1 minus H4. And similarly if we across the condenser, if you see, it will be H2 minus H3, and work transfer in the turbine is similarly applying control volume will be equal to H1 minus H2, and in the pump is H4 minus H3. So we know all the component, we can apply, can find out the efficiency. The efficiency will come out to be 1 minus H2 minus H3 by H1 minus H4. And again there is a term called back work ratio. So back work ratio is nothing but the net work which you are giving divided by the net work which you are getting. So pump work divided by the turbine work. So the ratio of work which you are generating is used to run the plant. So that's what this means. So this is an ideal case of Rankine cycle which you have saturated vapor, but because of practical difficulties, you cannot handle two-phase liquid in a turbine. So you try to avoid that, and you try to limit the dryness fraction. You need a you try to bring the dryness fraction close to 1. So, and the other ways of increasing efficiency of the Rankine cycle is by lowering the condenser pressure, or by increasing the superheat, or by increasing the boiler pressure. So in case of reducing the condenser pressure, this colored portion is your net increase in work. So but the lower limit on the condenser pressure cannot be lower than the saturation pressure corresponding to the temperature of the cooling medium. So that is the limitation on that. And because of this, because you are going to a lower condenser pressure, you are expanding the turbine to a lower pressure, and it you have a higher moisture content at the exit, so your dryness fraction basically goes down. You are doing this, but you increasing the superheat, your heat input increases, but in case of lowering the condenser pressure, you are again there is some additional amount of heat which you have to supply. And 3, you have to again supply more work, but this colored portion is the net work which you are getting. And then in this case you are avoiding lower dryness fraction, so your dryness fraction improves, basically you going to superheat. And other way of doing it is doing it in stages, where you increase multiple reheating, so that can improve your efficiency further. And your dryness fraction also improves. The other case is by increasing the boiler reheat. There this green portion is what you increase you get, and red portion is your decrease. But here again there is a disadvantage of lower dryness fraction. So the next cycle is a VCRS cycle, vapor compression refreshing cycle. So this again is equivalent to your Rankine cycle, but the only difference is, instead of the isentropic pump compression, you change it to isenthalpic process. So 1 to 2 is a compression, and this is a reversible cycle, reverse cycle engine. So it's a refrigerator. So 1 to 2 is a compression process, 2 to 3 is condensing, and 3 to 4 is isenthalpic expansion, and 4 to 1 is again heat addition. So isentropic process, isobaric, isenthalpic, and then isobaric. So compression process is nothing but H2 minus H1 can define, and then Q out is H2 minus H3, and Q in is H1 minus H4, and H3 is equals to H4. Using this, you can define a coefficient of performance, COP, of the system, which is nothing but your desired output divided by the work input, or the input energy input. So desired output is the heat in cooling which you get from 1 to 4. So Q in divided by the compressor work. So H1 it will come out to be H1 minus H4 divided by H2 minus H1. So that covers all the cycles which we studied. And then moving on to mixtures. So you know moles. Moles is defined as a mass divided by the molecular weight. So for any component, the number of moles of that component is equals to the mass of the component present divided by the molecular weight of that component. So Ni equals Mi by capital M. Capital M is the molecular weight. So you can define mass fraction as the mass of that component divided by the total mass. So if you have multiple mixtures, so mass of that, if you suppose you have oxygen and carbon dioxide, and you want to define mass fraction, the mass fraction of oxygen is mass of oxygen divided by the total mass of oxygen plus carbon dioxide. So mass of Mi divided by mass. So M is nothing but summation of individual component masses. Then the mass fraction summation is equals to 1. Then similarly you can define mole fraction. So mole fraction is number of moles of component divided by the total number of moles, and again your summation of each of the mole fraction will sum out to be equal to 1. So the molecular weight of the mixture is defined as your mole fraction into molecular weight, summation of that of all the components, so summation of yi into mi. So the product of mole fraction into molecular weight of all component gives you the molecular weight of the mixture. Similarly, the Dalton's law of partial pressure, it says that the pressure exerted by the individual component is equals to mole fraction into the total pressure. So Pi is the partial pressure of the gas equals yi into P, and the summation of the partial pressure is equals to the total pressure. So if it's nothing but P is common, summation of yi will become 1, summation of yi is 1. So summation of partial pressure is equal to pressure. And similarly for your mixture property, could be either internal energy, enthalpy, or entropy, is defined as summation of mole fraction into individual component energies or entropy. So yi into ui summation. And Cv, the specific constant volume, is again a summation of yi into Cv of that component, and Cp is summation of mole fraction of that component to Cp of that component. And if you want to find out gamma, so you cannot do summation of yi into gamma, you have to find out Cp and Cv of the mixture separately, and you have to find out Cp, the Cp of mixture divided by Cv of mixture. So that will give you the gamma of the mixture. So you cannot do gamma of mixture equal to summation of yi into gamma of I. That is wrong. You cannot do. So you have to find out Cp of the mixture. You have to find Cv of the mixture. Then you can find gamma of the mixture by Cp by Cv. So that covers the mixture portions. Then moving on to psychrometry. So psychrometry is the study of moist air. So you have a mixture of water vapor and air. So that gives you, so we can assume each of the component, water vapor or air or the moist air, has ideal gas, and you can apply ideal gas law. So that gives you P equal to nRT by V. N is the number of moles, R is the universal gas constant, so T by V. And you can apply A denotes the dry air, so P equal to NART by V. And similarly V denotes the water vapor, so PV equal to NVRT by V. And omega is the specific humidity. It says that mass of vapor, water vapor present in the per unit mass of dry air, so mv by ma. This if you write in terms of mole numbers, so you know mass, mole number is nothing but mass by molecular weight, so you can write mass as moles into molecular weight, so nv into molecular weight of water vapor into mole of air into molecular weight of air. So nv can be converted into molecular mole fraction dividing by your total number of moles, so that gives you molecular weight of vapor into molecular mole fraction of water vapor divided by molecular weight of air into mole fraction of air. So you can now write your molecular weight is nothing but equal to applying Dalton's partial law will be PV by P. This is proportional to your vapor pressure, your partial pressure. So PV divided by PA. So PA you can again find write the total pressure, and you can write it in terms of P minus PV. And this molecular weight of vapor by molecular weight of air gives you 0.622. If you substitute the values, you will get 0.622. So this will be the final expression which you can use it to solve. Specific humidity is 0.622 PV by P minus PV, where P is the partial pressure of water vapor. Then to know whether how much more water can the air accommodate or not, so use the degree of saturation was 5 or a relative humidity. you can say phi as yv by yv sat. So that says how much mole fraction of air is present at saturation, and yv sat, and yv is the mole fraction of water vapor present in the moist air. So that is given in terms of pressure as pv by p saturation pressure. P saturation is pressure is the saturation pressure corresponding to the temperature of the moist air. And your dew point is nothing but your saturation temperature corresponding to the vapor pressure of the water vapor, partial pressure of the water vapor. So from the steam table you can find out what is your dew point temperature, or you can find out from the psychrometric chart as well. And enthalpy of the moist air is defined as enthalpy of individual component divided by your mass per kg of dry air. So this is what you can straight away from the psychrometric chart also you can find out. So Ma into Ha plus Mv into Hv divided by Ma. So this gives you your specific enthalpy of dry air, plus omega is your specific humidity, which is Mv by Ma. So into enthalpy of vapor. Then moving on to the reaction question. So you have you can define air fuel ratio. Air fuel ratio is nothing but mass of air divided by mass of fuel. This you can also write it in terms of moles, which gives you moles of air divided by moles of fuel into molecular weight, so on. So this is what the expression will be: air fuel ratio in terms of mass equals air fuel ratio in terms of moles into molecular weight of air divided by molecular weight of fuel. And again, for any reaction, for any component, the enthalpy is defined as enthalpy of formation plus enthalpy at the temperature and pressure which you need to find out, minus enthalpy at the reference temperature and pressure. This is basically your NPT condition, which is 298 Kelvin and 1 atmosphere. And you can find out the straight away the change in delta H for that for your given T and P. You can find out the delta H, and the enthalpy formation can also be found out from the tables. And this gives you enthalpy as enthalpy formation plus the delta H. And similarly, entropy can be found out as SC at any temperature and pressure is your entropy at the reference point temperature minus R, the universal gas constant ln P, gas constant, not universal gas constant, gas constant to ln P by P reference. So for any chemical reaction, if you apply an energy balance, so this is similar to the first law which you get, just that you need to form, instead of enthalpy, it is your enthalpy of formation and in the delta H, and mass, this is all written in moles, so instead of mass you use moles. So Q by C, QCV by number of moles in feed minus W by NF equals summation of the number of moles of the product into enthalpy minus the reactant enthalpies. So if you have a closed system, then you need to do in terms of internal energy. So enthalpy will be internal energy, so we can use H equals to U plus PV. So you can use H minus PV in that case. So you have additional term of minus RT by summation of N. That is coming because of the ideal gas expression PV equals to nRT. So you are converting PV into nRT, and this basically Q minus W equals to summation of internal energy of the product minus internal energy of the reactant. That you are writing as H minus nRT. And the equivalence ratio is nothing but actual fuel ratio by your stoichiometric air fuel ratio. And coming to the end of the last week, which I covered yesterday, so you have chemical and phase equilibrium. So for any process, it ultimately goes to satisfy that your entropy is maximum, and if you have a fixed temperature and pressure for any given condition, that says that you need to have a minimum in Gibbs energy, So your dg is equal to 0. That gives you the equilibrium criteria. So that is corresponding to the stationary point or the minimum in the Gibbs energy. So in Gibbs energy, this can be written in terms of your chemical potential, so which is defined as dou g by dou n9. So at equilibrium criteria, this chemical potential of the component in each of the phases will be same. So G can be written as summation of Ni into Gi at any T and P. So again, mu I can be written as Gibbs energy of formation at any state point reference plus R T ln Pi by P reference. So Pi is again Dalton's pressure. You write Yi into P. So from this at equilibrium, you need to find out the equilibrium constant. Then equilibrium constant is nothing but your mole fraction of the component product raised to power their individual coefficient in the expression. If you write a reaction expression, the coefficient, so mole fraction raised to power their coefficient divided by the reactants mole fraction raised to power their coefficient into P by P reference raised to power the difference in the coefficients of the product minus reactant. So this gives you Q. So you can convert that into N also, number of moles. So you have to just multiply each of the component by N. So this is what you get. And finally, phase equilibrium criteria defines that your individual chemical potential should be equal. So G small g dash is nothing but the chemical potential. So chemical potential in each of the phases should be equal. So this is what mu dot A dash equals mu dot A. If you have two component mixture A and B, so A in phase 1 dash is equals to chemical potential in phase 2. So and then you have Gibbs phase rule, which defines number of degree of freedom, or which you have to define the system, which you fully defined system. So that is called F equal 2 plus N minus P. So that covers the whole thermodynamics. If you have any doubts, you can ask. I think I've covered what was covered in the 12 weeks. I'll try to cover most of it, I guess. If you have any doubts, you can ask. So if you don't have any question, then you can wind up the session. So this is the last class. And I don't know when your exams is, but if you have any questions on the thermodynamics course which you have attended, you can ask. Then we'll close the session. Thank you for joining and all the best for your exams.